Okay, welcome back. Happy Monday, everybody. Today is September the 12th, class number 3, our introduction to graphs and graphing utilities. Just loaned a bunch of graphing calculators out. One other thing to note, you'll see here project 1 is officially assigned as of right now. Somebody handed these things out, so make sure that everybody grabs one. It looks like this. This is project 1. Everybody have one of these? Project 1 is going to make extensive use of GeoGebra, which is a free piece of software that you'll either download on your home computer later on, or it's already on all the computers in the Math Studio here. And there are step-by-step instructions in the packet itself, in the project, that will help you with this brand new piece of software. So if you're not a computer person, you don't need to worry about it. There's instructions, there's screenshots, just follow the steps. And then if you want even more assistance and introduction to GeoGebra, there's this one-page reference sheet, so make sure you grab one of these as well. This just gives you some of the bare-bone basics, again, assuming you've never seen this software before. So go ahead and grab one of those. I think there were 2 other handouts. One of them is another one-page handout that says homework as assessment. Everybody have one? Homework as assessment. I don't remember where I read this. I think I found this online someplace. It talked about a real common mistake that many students apply when they do their math homework. And this one small change seemed to have a very big positive impact on a lot of people in this particular study. And it had to do with how you treat worked out examples as you are doing your math homework. And so it's really not something I'm going to reference again, but I saw it over the summer, and it just sort of, it seemed to maybe ring true with me, and so I figured I'd share it with you guys and see if it helps. So optional reading, it's only 1 page front and back. You won't lose more than 5 minutes by reading it, and you might gain a lot on the other end if you try the techniques here and they work for you. This is not on the syllabus. It's just a separate handout. Okay, was there a 4th handout? What did I miss? Oh yeah, the tips and tricks, right? Okay, so I gave you on the first class of the semester, I gave you here's how you log into My Math Lab, and here's some of the basics. Second class of the semester, I gave you a few more advanced things in terms of My Math Lab. This is the last My Math Lab handout I'm going to give you. It's supposed to make it so that you can work through these problems more quickly, more efficiently, and with fewer errors. For example, instead of moving your mouse over to the, what's the button when you say, yes, this is my answer? What's the button? Like check answer or something? Like instead of moving your mouse over there, which is honestly not, that's like a first world problem. It's not that big a deal. If you just hit the enter key, it's the same as moving your mouse over and clicking. And I don't know, I'm kind of nitpicky about little detailed time savers like that. So there's lots of good stuff. You can save yourself a lot of time over the course of the semester by using some of these easy to follow simple techniques, okay? So have a look at that later on. All right, project number 1, like I said, is assigned now. It is due September the 16th, which is this coming Friday. And so you've got, 4 days or so between now and then to do it. And I think I do take it late. There's some lateness penalty that I put in the syllabus, but I don't remember offhand what it is. But you want to try to get this thing done by Friday, if at all possible. One other thing about the My Math Lab homeworks. Again, the default is that the homework assignments are always due the start of the very next class. So the homework the material we're covering today, the homework will be due at the start of Wednesday's class. And in fact, the first 2 homework assignments are also going to be due at the start of Wednesday's class. I wanted to give folks a little bit of extra time to get logged into My Math Lab here at the start of the semester. But that 1-week deadline you had from the first assignment was atypical. From now on, it's going to be 48 hours after we cover is when things are due. Again, 10% penalty, which is not all that much, honestly, but get it done before the deadline if at all possible. Any questions about calendar stuff? Okay, so let's come back here. I think we're on page 11 here in the packet. So the preview exercises talked about the coordinate plane, also called the Cartesian plane. We had some coordinates written down here, so let's just get a couple of them. For example, C, what are the coordinates there? 0, 4. That's 0, 4. And then let's do one more, B. -3 and -1. It's good. It's supposed to be a review of plotting points, hopefully something we've all seen and are comfortable with. Then we also want to be able to take the coordinates and plot them. So for example, E, -4 and 2. So we go -4 left and then 2 up, and that right there is point B. Good? Okay. So number 2 gets a little bit deeper into that. It says we use the coordinate plane to help us visualize our relationship between two variables, which we often call x and y, and a graph is a set of all points that satisfy the equation, always written x first and then y second. Okay, so that's not all that exciting, that sentence, but we're going to be doing a lot of word problems this semester, and the relationships we're talking about are much more interesting than just, oh, here's an equation with x and a y in it. It's real data and real equations that we'll play with and answer interesting questions about. But for right now, we're just going to kind of go through the basics of the x's and the y's. So it says graph by plotting points, and so I'll just do a couple of these guys here. For example, if x is equal to 3, then we do 4 minus 3 squared, which is how much? Yeah, so that's 4 minus 9 is -5, and so then this is the point 3, -5. Yep. And so you plot your points here. So what do we get? 3, -5 is what we just said, and if we plug 2 in, do we get 0? 1 in, we get 3. Am I doing this right? And then a 4 up there, and then there, and then finally over here. Okay, that right there is a list of, what, 7 points. I messed something up. -2 is, -2 is 0, and then, yeah, I think I was off by 1. Is it there? How's that? Okay, good. So that is 7 points. Are those the only 7 points that satisfy that equation? No, how many are there? Infinitely many points. These are just a few representative points. If I wanted to graphically, think about what all infinitely many points look like, what would you do? Something my 5-year-old son loves to do at the restaurant on the little placemat. What do? Connect the dots, right? That's what you do. And so you draw something. Okay, so there are a few ways to actually connect the dots wrong, and I don't want you to do that because I take points off. So don't do this. Let's see, straight line there, 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 straight line there. That ain't it. Connecting the dots, this curve is a very smooth kind of thing, and it is not as simple as just connect every pair of consecutive points with straight lines. So draw something that is fairly smooth. The other mistake that I made here is what? No arrows. I just stopped. This graph doesn't just stop because I ran out of points that I picked. It goes forever, right? So let's do that one a little bit better. Oops, here. And so just connect smoothly. It doesn't have to be perfect. I missed a couple of points myself. I'm not such a stickler that you got to have arrows, but you got to make sure your graph extends all the way to the end of the graph paper, right? That's our way of saying it goes forever. But arrows are fine too. Okay, so that graph represents all infinitely many solutions to this equation right up here. So far, so good? Okay, let's say one more thing. This wasn't one of the questions here, but what word starting with S describes this sort of mirror image stuff? Symmetry, right? This graph is symmetric with respect to what line? The y-axis. This graph is perfectly symmetric over the y-axis. It looks exactly the same to the one side of that line as it does to the other. We'll be talking about that kind of symmetry later on this semester. And in particular, just given the equation that y equals 4 minus x squared, there's an algebraic way that we can figure out, yeah, it's going to be symmetric over the y-axis without plotting a single point. So that's coming later on. All right, let's move on to the next page. And we've got our demo. We'll do this together here. Okay, so first up is finding x and y intercepts of a graph. So it's vocabulary, but I think it's stuff you've seen before in a previous math class. The x-intercepts of a graph are the places where the graph crosses or intercepts the x-axis. X-intercept is where we hit the x-axis. Just going to go back real quick to this picture. How many places does this graph hit the x-axis? It's 2. So how many x-intercepts does it have? It has 2. And we can write down their coordinates, 2, 0, and -2, 0. We'll do that on the next page. Y-intercept is a place where the graph hits the y-axis. How many y-intercepts does this graph have? Just the one, and it has coordinates that we'll write down, 0, 4. We have there. Okay, so let's see here. It says write the coordinates of the x and y intercepts. Okay, so x-intercepts we said were 2, 0, and -2, 0. And then the y-intercept was 0, 4. Good. And I just want to point out a place where mathematicians have chosen the same single notation to represent two wildly different things. The point 0, 4, we all visualized it, we plotted it, it's fine, right? But didn't on the, I guess, last class, on Friday's class, didn't we talk about interval notation? And didn't we write things that looked exactly like parentheses 0, 4? And if I'm thinking about the number line, 0, 1, 2, 3, and 4, and 4. The 0, 4 in interval notation represents what? It's all the points from where to where? From 0 to 4. So we're talking about all these points in here. Do we include or exclude the endpoints? Exclude, because of the open parentheses. So like in when I used to take math classes way back when, it's before electricity. We would use open circles, and I think some places, as far as I know, that's still the standard. But like I said, your book in my math lab uses the parentheses. But anyway, 0, 4 looking like that, it means two really different things, and it better be clear from the context which one it is. So I just wanted to point out that we have two different notations. Sorry, one notation that means two really different things. Okay, how could we have found these special points, that is the two x-intercepts and the one y-intercept, without plotting the entire graph? All right, let's try the second one first here. It says to find the y-intercept algebraically. The y-intercept algebraically. Okay, thinking about this picture right here, the y-intercept again was this point. Now this point had two coordinates. This was a 0 and a 4. But suppose that the y-intercept of another graph, not this one, was this guy right here. What are the coordinates of that point? Yeah, 0 first and then -3, right? And do we see the commonality between those 2 points? And you could pick another, like you could say, you know, maybe this is the y-intercept of something else. What are the coordinates? 0, 1. And so do you see what's the same at every y-intercept? It's always x is 0. So this is now something that is like synonymous in my brain. Y-intercept, x is 0. I mean exactly the same thing for me. And so that's our process, is to find the y-intercept, we're going to let x equal 0. So let's come down here. To find the y-intercept, we let x equal 0. Always, always, always. So let's do it. In this case, the equation was y equals 4 minus x squared. And then we let the x equal 0. Notice I'm going to copy everything else except for that x. So it still looks like y equals 4 minus x squared, but instead of x, what are we putting? 0. And let's see, then we just do the arithmetic. 0 squared is 0. And so y is indeed equal to 4, which is exactly the y that we came up with by looking at the picture. And so that means that the y-intercept, our intercepts always have 2 coordinates. Where's the 4 go? That's the second, that's the y. It's really easy for students to miss that you picked an x at the very start of this process. What x did we pick? We picked 0. So those are the coordinates, right? And notice that what we just did there didn't rely on the graph, didn't rely on plotting points, didn't rely on any of that. Just the equation, and then this process, which is always to find the y-intercept, we let x equal 0. Okay, so that's how we find the y-intercept. Coming back to our picture, and now we'll change gears and think about x-intercepts. We'll just write down coordinates here. We'll do purple. So this guy right here is 2, 0. And this one over here, -2, 0. Do you see the commonality between those 2 points? The y is definitely 0. And even if the y-intercept for another graph were way out here, what are the coordinates there? 6, 0. And for sure, the y is equal to 0. And so again, this is something synonymous in my head. X-intercept, y is 0. They mean exactly the same thing for me. So to find the x-intercept algebraically, we let y equal 0. Okay, so let's do the algebra here. I'll rewrite the entire equation in its original form. Y equals 4 minus x squared. And then the process we just said is to let y equal 0, so let's do that. Notice that everything gets copied except the y becomes what? 0. So one single change. I'm probably going to say this a bunch during the semester, but a lot of mistakes that I see math students make are because they try to make multiple changes in one step. And for me, one step, one small change. Lots of successful mathematics is copying almost everything down, and then you just make the one small change. So that's all we did. The y became 0. Okay, so we solved this equation. You might actually be able to just look at that and know what the answer is. How much is x? It's 2, right? I mean, 4 minus 2 squared is equal to 0. Well, I'd really like a process, even though we can see maybe 2 is going to work here. So how about we add the x squared to both sides? Can we do that? So I'll write that. Let me add x squared here, add x squared there. And so then the next equation says x squared equals 4. And again, even if you can just look at it and know the answer is 2, let's come up with an algebraic thing that we're doing to both sides of the equation. Square root, right? You want to get your x and you have x squared, you take the square root. So it's something that you're actively doing to both sides of the equation. And so we get here x equals 2, right? Except we're not done. There's nothing wrong with what we did, I guess. But how many answers were there to the x-intercept problem? There were 2. How many did we just find? 1. That's not satisfactory, right? And so there's this really subtle thing that maybe you remember from a previous algebra class is when you take the square root of both sides of an equation, you have to put something in. You got to put in a plus or minus. And it is just so easy to forget to do that. Right at that stage right there, you put in a plus or minus. And so there's your 2 answers. X is 2 and X is negative 2. Now I can say until I'm blue in the face, don't forget, gang, when you take the square root of both sides of an equation, put in the plus or minus, and most of us are still going to forget to do that. And so how about another technique? How about we go back to the original equation way back here? I'm going to copy it again. 0 equals 4 minus x squared. That will give you a method that will not lose, that won't rely on you remembering that simple, easy to forget plus or minus. Ivy? Yeah, you could do that. Yeah, and I think that'll end us kind of back on the same type path that we were on before. What we're going to do, copy the left-hand side, 0 equals, and we're going to factor this right-hand side. 4 minus x squared is a difference of 2 squares. And we talked about this kind of pattern on the first day of the semester. 2 numbers that are the same that multiply to 4, 2 and 2. 2 things that are the same that multiply to x squared, x, and the signs, 1 plus, 1 minus in any order. And that's our difference of 2 squares pattern, right? And then we get to solve 2 much simpler equations. Either 0 is equal to the thing in the first parentheses, 2 plus x, or 0 is equal to the thing in the second parentheses, 2 minus x. And when you solve the first equation, how much is x? Negative 2, that's the negative that we missed before. And when you solve the second equation, how much is x? Positive 2. And so factoring might feel like it's more annoying, but I think it's more reliable, less likely to forget that plus or minus. Either way, we've got 2 answers here, 2 comma 0 and negative 2, 0. Yeah, I think it works out. No, you gotta do maybe 2 steps to solve that equation for x. Yeah, honestly, if I were solving this equation for x, I would not move the 2. What would I do? I move the x, add x to both sides, and we win. X equals 2. Right? Okay, one other thing to say about intercepts. just as a way to remember the process here, to find the, let's highlight here, to find the x-intercept, we let y equal 0. To find the y-intercept, we let x equal 0. And the way that I remember that is to find an intercept, you let the other variable equal 0. You want to find the x-intercept, let the other letter, the y, be 0, and vice versa. Got it? Okay. All right, here is a very brief intro to graphing calculators or graphing utilities. Now, I know I just traded each of you guys, or almost all of you, a calculator. You'll have plenty of time to use the calculator in the activity, but I actually want you to put them down on the tables right now and not touch them, because I'm going to go through this right now, and if we were to wait for all of you to be able to follow the steps, some of you are already experts at this particular piece of technology and will have nothing to do, and for others, it's going to be kind of fast no matter what we do. And so I just find when it comes to technology, better to just have me zip through this once, and then you guys can go at your own pace, whatever that is, okay? And I promise there's lots of expertise at each of your tables, so we'll get through this. All right, let's do the same kind of thing that we just did, but we'll use the graphing calculator here. So we are going to graph, clear. Okay, so we're going to graph y equals 4 minus x squared. So the first thing that I did, and I'll try to do this with the mouse so that if you happen to watch this video later on, you'll see what buttons we're pushing. So we're first going to press y equals, which is up here, brings up this crazy looking menu. We're going to enter the equation, this 4 minus x squared. So 4 minus x squared, there's the x squared button. And then we're going to press the graph button. Now, when you press the graph button, you might get a nice looking window, which is what this one is. But for example, you might get something that is wildly different. Let's just look at it here. How does that look compared to what you plotted? Looks quite similar. So that's good there. If you wanted to change the window, for example, this graph goes off the bottom of the screen. Yes, right. It doesn't go off any of the other sides of the screen. It goes off the bottom. So if I go into window, I can look in here, and for example, y min, that's the minimum y that we are seeing. If I make that minimum y even smaller, then I will see lower on the graph. And so for example, if we scroll down here and change this to like -50, then we're going to see a lot lower. We're going to see a lot more of this thing way down here at the bottom. Okay. Personally, I don't like when my y-axis or either axis is like all dark and thick like this is. Anybody know why it's so thick? It's not so we can see it better. We know? Yeah. Yeah, it's a lot of hash marks. In fact, so many that it just looks like it's shading in the whole y-axis. And so if, again, you're in window, the spacing between the hash marks is given by the scale, y scale or x scale. And so, for example, if I said, hey, why don't you show me a hash mark every 10, then I get something that I can read, and it's just easier to look at, I think. Okay, so you can mess around with the scales. It says here that the way that we're going to write this kind of thing down is this. There's a little x between the two sets of numbers in brackets. -10, comma 10, that's the x min and the x max. And the 1 there is the x scale. And then after the x, same thing, but it's all y numbers, okay? And so this is just like, this is our standard format. And so if you ever need to, like if you see something like this, just come back to this page. It tells you what to do. Okay, and you're also welcome to zoom in and zoom out. You can play around with that later. And then the only other thing we're going to do is just quickly look at GeoGebra, which is this free piece of software here. One thing, I really like GeoGebra, but I think that the default for the font size is way too small. So feel free to change that to something that you can actually see. I'm going to come down here, this thing called the input bar. On my screen, it's on the bottom. If you use the GeoGebra app, it might be up on the top. It'll hopefully be obvious where this thing is. And we just type in just like it was, y equals 4 minus x, and then the symbol for power is the caret. It's on top of the 6 on the keyboard. And there it is, y equals 4 minus x squared. And one really powerful thing about GeoGebra that makes it better than the graphing calculator is that it's really easy to move the thing around. If you just click this thing that looks like the axes, you click in any blank space and you can drag. And you can also highlight one of the axes. See how the cursor changed from the hand to this double arrow thing? And so if I now click and drag here, I'm pulling the thing apart horizontally or smushing it. And again, I can do the same thing with the y-axis. And so it's just a lot easier to get the particular view that you're interested in using GeoGebra, okay? All right, any questions on any of that stuff? All right, so activity starts on the very next page. This is where you're going to use your graphing calculators, and I will walk around.